Welcome to this problem walkthrough on LeetCode problem number 754, titled Reach a Number. In this session, we'll explore the problem, analyze its requirements, and break down various approaches to solve it efficiently. Let's dive in. In this problem, you are standing at position 0 on an infinite number line, and your goal is to reach a specific target position called target. You can move either to the left or to the right, and the number of steps you take increases with each move. For example, on the first move, you take 1 step, on the second move, you take 2 steps, and so on. Your task is to find the minimum number of moves required to reach the target position. Let's look at an example to understand this better. If the target is 3, the output is 2, meaning it takes 2 moves to reach the target. We'll break this down in the explanation next. For the target value of 3, the first move involves taking 1 step to the right, moving from position 0 to position 1. Then, on the second move, you take 2 more steps to the right, moving from position 1 to position 3. This gets you to the target in just 2 moves. Now consider a different example where the target is 2. In this case, the first move is again 1 step to the right, bringing you from position 0 to position 1. On the second move, you take 2 steps to the left, moving from position 1 to position -1. Finally, on the third move, you take 3 steps to the right, reaching position 2. This means that it takes 3 moves to reach the target of 2. Let's examine another example with a target of 7. On the first move, you take 1 step to the right, moving from position 0 to position 1. On the second move, you take 2 steps to the right, going from position 1 to position 3. On the third move, you take 3 steps to the right, reaching position 6. On the fourth move, you take 4 steps to the left, moving from position 6 to position 2. Finally, on the fifth move, you take 5 steps to the right, arriving at position 7. So, it takes 5 moves to reach the target of 7. It's also important to keep in mind the constraints. The target can range from -10 to the power of 9 to 10 to the power of 9, and the input will always be valid. There are a few edge cases to consider for this problem. First, if the target is negative, the movement pattern remains symmetric. This means the solution for a negative target, like -3, is the same as for its positive counterpart, 3. The steps would just reverse direction. Second, if the target is 0, no moves are needed since you're already at position 0. For large targets, the solution must be efficient and able to handle numbers as large as 10 to the power of 9, as trying every possible move would be computationally expensive. Lastly, for small targets like 1, the solution should still calculate the exact minimum number of steps required. These considerations ensure the approach works for all possible inputs. To begin, let's consider the brute force approach, which involves simulating every possible sequence of moves. Starting from position 0, we explore all combinations of taking steps to the left or right, incrementing by 1 step at a time. While this approach seems intuitive, there are some critical drawbacks. First, the number of potential paths grows exponentially as we take more steps, making it computationally infeasible for large target values. Second, keeping track of all reachable positions at each step consumes a significant amount of memory. As a result, the time complexity is 2 to the power of n, where n represents the number of steps, and the space complexity is also 2 to the power of n. This makes the brute force approach impractical for solving the problem efficiently. Now, let's move to a more efficient and optimized approach that leverages mathematical insight. Instead of simulating paths, we focus on the cumulative sum of steps. If we take k steps, the total distance covered is given by the formula s equals k times k plus 1 divided by 2. Our goal is to find the smallest k such that the sum s is greater than or equal to the absolute value of the target, ensuring we consider the positive version of the target. Additionally, the difference between s and the target must be even, as this allows symmetric adjustments by flipping steps from positive to negative. This insight reduces the problem to iteratively calculating s for increasing values of k, stopping as soon as both conditions are met. The sum of the first k numbers grows quadratically, so we can find the solution in sqrt, target, time, using only a few variables, which keeps space complexity at 1. Analyzing the complexity of this approach, we see that the iterative process runs in sqrt, target, time, as we only compute s for potential values of k up to a point. Space complexity remains O1, since no additional data structures are required, only a few variables. An alternative to this iterative approach is using binary search to directly find the smallest k that satisfies the conditions. Binary search reduces the number of iterations, achieving a time complexity of O log target. However, verifying that the difference s minus target is even introduces additional logic, making the implementation more complex compared to the straightforward iterative method. While binary search may be faster in some cases, the trade-off in simplicity is worth considering. Given these options, the chosen strategy is to use the iterative approach based on mathematical insight. The brute force method is clearly infeasible due to its exponential time and space requirements, even for moderate target values. Between the iterative and binary search methods, the former stands out for its simplicity and ease of implementation. Both approaches share similar space complexity, but the iterative solution avoids the additional complexity of verifying conditions during binary search. Ultimately, the iterative method strikes a balance between efficiency and simplicity, achieving an O-SQRT target solution with minimal memory usage, making it well suited for this problem. To summarize, this problem highlights the power of mathematical reasoning over brute force simulation. The key realization was understanding the arithmetic progression of steps and leveraging symmetry, which allowed us to adjust the final position by ensuring the difference between the sum and the target is even. This mathematical approach not only eliminates the inefficiencies of brute force but also demonstrates the elegance of solving problems by analyzing their structure. By reducing the complexity to O-SQRT target, with minimal space requirements, we see how leveraging insights can lead to both efficient and clean solutions. To solve the reach a number problem using the brute force approach, we begin by fully understanding the problem setup. The task is to determine if we can reach a specific target position, t, starting from position 0 on a number line. At each step, we can either move to the right by the step number or to the left by the same amount. For example, on step 1, we can move +1 or -1, on step 2, we can move +2 or -2, and so on. The goal is to figure out if t is reachable and identify how to achieve it. To simulate this, we define a recursive process that explores all possible moves. The recursive function takes two parameters, the current position on the number line and the current step we are on. A key part of this algorithm is the base case. If the current position matches the target, we know it's reachable, so we return true. Conversely, if the current step exceeds a reasonable limit, such as 10,000 steps, we stop the recursion and return false to avoid infinite loops and excessive computation. The recursive process continues by exploring both possible moves at each step. This means we simulate moving to the right by adding the current step to the position, and we simulate moving to the left by subtracting the current step. For each of these moves, we call the recursive function again, passing the updated position and incrementing the step. If either of these recursive calls eventually returns true, it signals that the target is reachable, and this result propagates back up the recursion chain. To implement this brute force simulation, we initialize the recursive process starting from position 0 and step 1. This ensures we evaluate every possible combination of moves. Finally, the algorithm outputs whether the target t is reachable. If the function returns true at any point, we know the target can be reached. If the recursion exhausts all possibilities without finding a solution, we conclude that the target is not reachable. The brute force approach provides a way to solve the problem, but it has significant limitations. One major insight is the exponential growth of the state space. Since each step has two possible moves, the algorithm explores 2 to the power of n combinations, where n is the number of steps. This exponential growth results in a time complexity of O2 to the power of n, which becomes computationally expensive as n increases. Another important observation is the symmetry in movement. Because the number line is symmetric, many states overlap or repeat. For example, reaching position 3 can happen through multiple combinations of moves, yet the brute force approach redundantly evaluates these states again and again. Moreover, without memoization, the depth-first search re-evaluates the same state multiple times. This inefficiency significantly increases the number of redundant calculations, slowing down the process and consuming unnecessary computational resources. In terms of data structures, the brute force approach relies heavily on the recursive call stack. Each recursive call adds to the stack, tracking the sequence of moves being simulated. The maximum depth of this stack is determined by the maximum number of steps, and for large values, this can lead to stack overflow errors. Additionally, the brute force method does not use any optimized storage like a hash map or table-to-cache intermediate results. Without this auxiliary structure, the algorithm cannot avoid redundant computations, further contributing to inefficiency. Despite its inefficiencies, the brute force approach works because it systematically explores all possible move sequences. The recursive exploration ensures no potential solution is overlooked. The base case evaluation guarantees the recursion halts when the target is reached or when it exceeds the step limit. By simulating both positive and negative moves at every step, the algorithm ensures that all paths are considered, even though it lacks optimization. To improve the brute force approach, several optimizations can be implemented. First, memoization can be introduced. By storing the results of previously computed states, such as the outcome of a specific position and step combination, we can avoid redundant calculations, drastically improving efficiency. Another optimization involves pruning unnecessary paths. If a position exceeds a plausible range, such as being significantly larger than the target plus a buffer, we can terminate the recursion early. This reduces the number of explored states. Additionally, the symmetry of movement can be exploited. Since the number line is symmetric, negative positions can be treated as their positive equivalents, effectively having the search space. These optimizations transform the brute force approach into a more efficient and practical solution, making it better suited for handling larger inputs while maintaining correctness. This solution addresses LeetCode problem number 754, reach a number. The problem asks us to determine the minimum number of steps required to reach a given target on a number line, starting from position 0 and moving either left or right by an increasing step size. The key insight is that the problem exhibits symmetry and can be tackled with a mathematical approach instead of brute force. Explanation of the code. 1. Convert target to positive. The first line of the function ensures that the target is positive. Since the number line is symmetric, the steps required to reach T or T are identical. This reduces the problem to handling positive values only. 2. Initialize variables. Step tracks the current step number. Sum_so_far maintains the cumulative sum of steps taken. This represents the position on the number line. 3. Increment steps until conditions are met. The while loop ensures that two conditions are satisfied. The cumulative sum_so_far should be greater than or equal to the target. We must at least reach the target. The difference between sum_so_far and target must be even. This is because flipping a step, changing it from plus to dash, adjusts the sum by an even amount. If the difference is odd, it is impossible to reach the exact target. The loop increments step and adds it to sum_so_far until both conditions are met. 4. Return the result. Once the conditions are satisfied, the function returns the number of steps taken. Efficiency. This solution is highly efficient with a time complexity of O, sqrt, t, where t is the target, as the sum of steps grows quadratically with the number of steps. It avoids a brute force simulation and leverages mathematical properties to find the result swiftly. This implementation handles all edge cases, including small targets, large targets, and negative inputs, making it robust and production-ready. This is the Java implementation of the reach a number problem from LeetCode. The logic mirrors the Python solution, converting the target to its absolute value to leverage symmetry, then incrementing steps while ensuring the sum meets the specified conditions. Key differences include Java's type declarations, use of math.abs for absolute values, and a structured class definition. To solve this problem, we start by initializing the necessary variables. Since the target is already positive, we set target equals 3. We then initialize step to 0 and sum_so_far to 0, which will keep track of the current step and the cumulative sum of steps, respectively. In the first iteration, we increment step to 1 and add it to sum_so_far, resulting in sum_so_far equals 1. At this point, we check if sum_so_far is less than the target. Since 1 is less than 3, we proceed to the next iteration. In the second iteration, we increment step to 2 and update sum_so_far to 3. Now, we verify the conditions. Sum_so_far is greater than or equal to the target, and the difference between sum_so_far and the target is divisible by 2. Both conditions are satisfied, so we terminate the loop. The minimum number of steps required to reach the target of 3 is 2, as the sum of the steps, 1 plus 2, equals 3. Now, let's consider the target of 5. Again, since the target is already positive, we set target equals 5. We initialize step and sum_so_far to 0. In the first iteration, we increment step to 1 and add it to sum_so_far, giving us a total of 1. Since sum_so_far is still less than the target, we continue. In the second iteration, we increment step to 2, resulting in sum_so_far equals 3. This is still less than 5, so we proceed. In the third iteration, step becomes 3, and sum_so_far increases to 6. Now, sum_so_far is greater than the target, but the difference between sum_so_far and the target, which is 1, is not divisible by 2. This means we cannot yet reach the target, and we need to continue. In the fourth iteration, we increment step to 4 and update sum_so_far to 10. At this point, sum_so_far is greater than the target, and the difference between sum_so_far and the target, which is 5, is divisible by 2. Both conditions are satisfied, and we can terminate the loop. For this example, the minimum number of steps needed to reach the target of 5 is 4. The sequence of steps, 1 plus 2 plus 3, 2, adjusts the total to match the target value. Now, let's examine the case where the target is minus 2. Since the target is negative, we take its absolute value, resulting in target equals 2. We initialize step to 0 and sum_so_far to 0. In the first iteration, we increment step to 1 and update sum_so_far to 1. Since sum_so_far is less than the target, we proceed. In the second iteration, we increment step to 2, resulting in sum_so_far equals 3. Now, sum_so_far is greater than the target, but the difference, which is 1, is not divisible by 2, so we continue. In the third iteration, we increment step to 3, increasing sum_so_far to 6. At this point, sum_so_far is greater than the target, and the difference between sum_so_far and the target, which is 4, is divisible by 2. With both conditions met, we terminate the loop. The minimum number of steps required to reach minus 2 is 3. The sequence of steps, 1 plus 2 1, gives a sum of 2, and by symmetry, we can apply this to negative targets as well. This demonstrates that the algorithm effectively handles both positive and negative targets through the same process, with the only adjustment being the use of the absolute value for initialization. The time complexity of this solution is O, sqrt, target, and this stems from how the algorithm determines the minimum steps needed to reach the target. It begins by iterating a variable, step, starting from 1, and incrementally adds these values to a cumulative sum_so_far. The loop continues until two conditions are satisfied. First, the cumulative sum must be greater than or equal to the target, and second, the difference between the cumulative sum and the target must be even. This even difference ensures that flipping the sign of certain steps can adjust the total to exactly reach the target. Now, the sum of the first n natural numbers is given by the formula n asterisk, n plus 1/2. To find the smallest n where the cumulative sum meets or exceeds the target, we solve the inequality n asterisk, n plus 1/2 equals target. This simplifies to n approximately equal to the square root of 2 times the target. As a result, the loop runs roughly sqrt, target, iterations in the worst case, since step grows linearly with each iteration. This analysis applies to the best, average, and worst cases, making the overall time complexity O, sqrt, target. The space complexity of the solution is O(1), meaning it uses a constant amount of memory no matter how large the input is. This efficiency comes from the fact that the algorithm only employs 2 integer variables, step to track the current step count and sum_so_far to compute the cumulative sum. Both of these variables occupy constant space. Additionally, the input target is simply converted to its absolute value at the start, which doesn't require any extra memory beyond the input itself. The algorithm avoids the use of data structures like arrays or lists, and it doesn't rely on recursion, both of which could increase memory usage. Consequently, the algorithm's memory footprint remains constant, leading to a space complexity of 1. Examining the time complexity further, we can see how this optimized approach compares to a naive solution. A brute force method might involve simulating all possible combinations of step directions, either positive or negative, to reach the target. This would require exploring the full power set of steps, which results in an exponential time complexity of 2 to the power of n. In contrast, the optimized solution leverages mathematical properties of sums and parity. By reducing the problem to finding the smallest n that satisfies the inequality n plus 1/2 equals target, it avoids the combinatorial explosion of the naive approach. The key insight here is that the loop terminates when the cumulative sum satisfies both the conditions that it is greater than or equal to the target, and that the difference between the sum and the target is even. Since the cumulative sum grows quadratically with the number of steps, this allows us to approximate the number of iterations as proportional to the square root of the target. Thus, the optimized solution achieves a time complexity of sqrt target. In summary, the solution to the reach a number problem is both time and space efficient. The time complexity is sqrt target, as the algorithm iteratively computes the smallest number of steps required using a mathematical approach. The space complexity is 1, as it only uses a constant amount of memory regardless of the input size. By avoiding the exponential growth of a naive solution and leveraging the properties of sums and parity, this optimized approach provides a significant performance improvement, making it well-suited for handling large inputs efficiently. When solving the reach a number problem, there are several common mistakes to watch out for. First, overlooking negative steps is a frequent error. Remember, moving backward by taking a step above can sometimes be essential to reach the target. Ignoring this option can limit the solutions you explore. Another issue is using inefficient recursion without memoization. Pure recursion recalculates the same results repeatedly, leading to exponential time complexity, which is impractical for larger inputs. Additionally, failing to prune unnecessary states can waste a lot of computational resources. For example, exploring paths that exceed the target or revisit the same state multiple times slows down the algorithm significantly. Lastly, incorrect base cases in recursive solutions can cause infinite recursion or wrong results. It's crucial to define clear and accurate stopping conditions to ensure your solution works correctly. Another common pitfall is overlooking edge cases. Examples include scenarios where you start at the target, when the target value is extremely large or small, or when specific constraints like step limits come into play. Missing these edge cases can lead to runtime errors or incorrect outputs, so always test for them. Now, when preparing for interviews, there are a few key insights to keep in mind. Problems like these often benefit from combining recursion or depth-first search with memoization to efficiently explore solutions. For problems involving both positive and negative moves, think about symmetry. Can the problem be simplified by focusing on absolute values or relative offsets? Dynamic programming is another powerful tool for tackling state transition problems. Clearly identify how you represent states and transitions in your DP solution. Lastly, be ready to discuss trade-offs during interviews. For example, explain why a brute force approach doesn't scale and how optimizations like pruning or memoization can make your solution more efficient. This problem also shares similarities with several related LeetCode problems, which can help you build a deeper understanding. For instance, LeetCode 494, target sum, involves adding or subtracting numbers to achieve a specific target sum, making it closely related in concept. Another example is LeetCode 377, combination sum 4, which focuses on counting combinations of numbers to reach a target. Similarly, LeetCode 416, partition equals subset sum, requires dividing an array into subsets with equal sums, emphasizing dynamic programming techniques. Finally, LeetCode 322, coin change, involves finding the minimum number of steps to achieve a target sum, which is often compared to jumping problems. Practicing these related problems can strengthen your skills and improve your ability to recognize patterns across different scenarios. Now let's discuss some alternative approaches and their trade-offs. A brute force simulation is the simplest to implement but is computationally expensive, often having a time complexity of O(2 to the power of n, or worse. It's only suitable for very small inputs and is mostly useful for gaining initial intuition about the problem. Recursive backtracking with pruning is more efficient than brute force but still risks high complexity unless combined with memoization. It's a good option when memoization is too complex to implement right away. Dynamic programming, on the other hand, is typically the optimal approach. While it requires extra memory for a DP table, it achieves much better time complexity, such as n*target, making it ideal for handling large inputs. Finally, breadth-first search, or BFS, ensures shortest path solutions but requires careful tracking of visited states to avoid cycles. BFS is particularly well-suited for problems where minimizing the number of moves is the main goal. Understanding the strengths and weaknesses of each approach will help you choose the right one depending on the constraints of the problem. Thank you for joining me on this walkthrough of the Reach a Number problem. We covered the problem's requirements, analyzed different approaches, and saw how a mathematical solution stands out for its efficiency. Remember to apply these concepts in similar problems to strengthen your skills. If this was helpful, don't forget to like, share, and subscribe. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!